Good morning, everybody. I hope everybody is doing good. Any questions before we start? Can somebody type in the chat? I want to make sure if chat is working. I mean, you can just type hi or anything. Okay, cool. Thank you. Hello. Okay, so I'm gonna do screen sharing. So yesterday we covered integral test. Let's quickly recall the integral test. If a corresponding function to a sequence, let's say f, if it is positive, decreasing, and continuous on the interval from 1 to infinity, then we can benefit from the integral test, which basically states that if the yes, yeah, it's on the canvas. Yeah. So these are the lecture notes. I mean, these are the papers I'm writing on. I directly scan them and post on Canvas. If you want to get to the links, then it will be, again, Canvas, Files, and then Zoom. And if you click on Zoom, you'll see a Word file called Zoom meeting links. Okay, please regularly check both of these folders so you can keep up with the class more easily. Any other questions? Okay, then, yeah, as I said, we covered integral tests. We pretty much finished the applications of integral test. Today, we're going to see the estimating the sum of a series using integral test. So let's start. Suppose we've been able to, this is still 11.3. This is the continuation of 11.3. Suppose we've been able to show the series AN is convergent. using integral test. Now we want to find an approximation to the sum. We want to estimate the sum. Let's call it S, the sum S of the series. I'll explain what it means. It means that if you add all the terms up of if you add up all the terms of a sequence, in other words, the sum of the series, it gives us S. Then the remainder Rn is the error made when Sn, the end partial sum. What does end partial sum mean? It means sum of the first n terms. Is the remainder Rn is the error made when Sn, the end partial sum, the sum of the first n terms, is used as an approximation. To the total sum, to the actual sum. So let's try to understand what this means. S is, which is the actual sum, is sum of all terms. A1 plus A2 plus A3, and it keeps going. There's somewhere an plus 1, the n term, n plus 1 term, and it keeps going. And Sn, which is the end partial sum, is from 1 to n, the sum of first n terms, A1, A2, up to an. Now, if we're trying to find the error made in approximation, it's pretty much the difference between the actual sum, the real sum, and the approximation we're using. So S is the actual sum, S is the sum of the all terms, and Sn, the end partial sum, is the estimation we're using. So if you subtract Sn from S, it will give you the error, or in other words, the remainder Rn, which is S minus Sn, which is first n terms will get cancelled. You'll have a n plus 1, a n plus 2, and this is going to be less than the integral of f from n to infinity. And here is why. So f is a positive decreasing and continuous function. Remember, we're using integral test to show the function, show the improper integral, so the series is convergent. So if you use the right endpoints to approximate the area under the curve, it's going to be a n plus 1. This is going to be a n plus 2. And as you can see, the sum of a n plus 1, a n plus 2 will be less than or less than or equal to the integral of f from n to infinity. So this is the first equality we have. And the second one, similarly, now if we use the left-hand points to approximate f, and this time the area of rectangles will be larger than the area under the curve f. A n plus 1, a n plus 2. So now we can write a n plus 1 plus a n plus 2 is greater than the integral of f from n plus 1 to infinity. Now we can clearly state the remainder estimate theorem. Let's sum up what we did. Suppose f is corresponding function to the sequence ak or an, doesn't matter, where f is continuous, positive, and decreasing. These are the conditions of integral test, remember, where x is greater than n, and the series an is convergent. If we represent the error made approximating s with Sn, in other words, Rn is s minus Sn, then we can write the integral of f from n plus 1 to infinity less than or equal to Rn, as we just found, and less than or equal, Rn is less than or equal to from n to infinity. And also, any questions so far? If you add Sn to both sides, this is what happens. If you add Sn to Rn, Rn plus Sn, in other words, the approximation plus the error, we're gonna get you the actual sum S. So then the actual sum will be in the interval Sn plus the integral of f from n plus 1 to infinity, and Sn plus from n to infinity f. So this is the remainder estimate theorem for the integral test. Now let's move to an example and it will make more sense. There are 3 parts: estimate, the maximum error, involved in approximation to the sum of the series one over n cubed by using first n terms. And then how many terms are required to ensure that the sum is accurate within points 0005. And the last part, estimate the sum of the series estimate the maximum. Part A, estimate the maximum error involved in approximation to the sum of the series 1 over n cubed by using first n terms. And part B, how many terms are required to ensure that the sum is accurate within 0.0005. And part C, estimate the sum of the series 1 over n cubed. So you will need calculator to solve this problem because it involves a lot of calculations with decimal numbers. So let's start with part A. We know that the error is always less than or equal to the integral of f from n to infinity. Okay, that's what the remainder estimate theorem for the integral test states. So let's try to calculate this integral from n to infinity. What is the corresponding function? Our series is 1 over n cubed, then the corresponding function is going to be 1 over x cubed dx, right? So let's try to integrate this guy, which shouldn't be that bad. This is an improper integral, so then limit as t goes to infinity from n to t, x to the power of -3 dx. the entire derivative of x to the power of -3 is x to the power of -2 over -2 from n to t. So we can pull out the -1/2. We can pull out -t. So you will have as limit t goes to infinity, t to the power of -2 minus n to the power of -2, which is going to give you t to the power of -2 is t goes to infinity, it's going to be 0. So then you'll pretty much have -1/2 times -1/n squared. Long story short, 1/2n squared. Okay, so it turns out Rn is less than or equal to 1/2n squared. We'll actually use the spec both in A and B. Now, in the first part, it says, what is the error if you use 10 terms? I mean, what is the maximum error if you use 10 terms? So it's going to be 1/2 times 10 squared. So then we say, let's say if we use 10 terms to approximate, in other words, if we just add up the first 10 terms of the series, maximum error is 1/200. And what is 1/200 is 0.005, I think. Yeah, and that's it. Any questions so far? Okay, and the part B, states that how many terms are required to ensure that the sum is accurate within 0.0005. So this time we're given an error and we're asked to approximate the actual sum within that error. Okay, so I think what we know is, we know that the error is always less than the integral of f from n to infinity. Okay, and we want this error to be, we want Rn to be less than 0.0005. So then we can just put 0.0005 over here, and this will make sure that Rn or error is less than the given number in the problem. Okay, and we know that from here, we know that this is 1/2n squared. So this is pretty much the inequality we should solve. Right? So then let's solve it for n. What is 0.0005? I would suggest you to turn it to a fraction. I think it's 5 over 10,000. Yeah. And then there are a lot of things you could do. I would say simplify 5 and 10,000. It's going to be 2,000, and simplify 2 and 2,000. So it turns out 1,000 is less than n squared if you do diagonal product. So now the question is, what is the smallest n that satisfies this inequality? So try to think of an n whose square is greater than 1,000. For example, if you think of 30 squared is 900. It's close. If you calculate 31 squared, I think it's still less than 1,000. But if you calculate the square of 32, you'll see that it's greater than 1,000. So we will need at least 32 terms. Another way to see that, you can just take square root of both sides. And you'll see it's, if you use your calculator, I think 31.6. So n must be, to have an error that is less than or equal to 0.0005, n must be greater than 31.6. You know, n is the number of terms. So we should have at least 32 terms to make sure our error is not larger than 0.0005. So let's clearly write that. We need, say n is 32. We need at least 32 terms. No, you're doing diagonal multiplication, right? So 1,000 is going to be on the left, n squared is going to be on the right. Doesn't make sense? Yeah, no problem. So we need at least 32 terms to make sure the error is within 0.0005. Any questions so far? One question you might ask, how are we supposed to do these calculations without calculator? Now, there are 3 possibilities. First possibility, there won't be any questions like that in the exam. I bet that will be your preference. Second possibility, you might be allowed to use calculator in the third test. And the third possibility, which is the most likely one, you will be given very easy numbers to calculate. So instead of 0.0005, imagine you're given 0.25. It's much easier to calculate. Okay, there's part C. Let's finish part C. Unless there are questions. So this time we're going to use the formula that gives us an interval or an inequality for the actual sum S. So basically, we're going to add up we're going to add Sn to the right-hand side and the left-hand side of the original remainder inequality. This is what I mean. So Sn, I think in the problem, okay. So we used the first 10 terms in part A. So what does Sn mean? S10 mean? It's the sum of the first 10 terms. In other words, 1 over 1 cubed, 1 over 2 cubed, 1 over 10 cubed. And if you calculate that, you'll see is 1.197,532. And this guy right here, you know that it's from 11 to infinity 1 over x cubed dx, and we found the integral of 1 over x cubed dx as 1 over 2n squared, and here we have 11 as n, so it's going to be 1 over 2 times 11 squared. Which is 1 over 242. And this one similarly will be 1 over x cubed dx, which is 1 over 2 times 10 squared, which is 1 over 200. Now let's sum up. It will be 1.197,532 plus 1 over 242. Obviously, we need calculator for that. Less than or equal to s, and s is less than or equal to 1.197,532 plus 1 over 200. And if you calculate these guys, you'll find that 1.201,664 and 1.202,532. So this is our approximation for the actual sum. Any questions about any of the parts? That's the sum of the first 10 terms. That's the sum of these guys. 1 plus 1 over 8 plus 1 over 27. If you keep adding them up all the way to 10 cubed, By the way, this is a terrible 10 cube. I'll fix that. So the sum of these 10 terms, starting from 1, and then 1 over 2 cube, which is 1 over 8, and then 1 over 3 cube, which is 1 over 27, and all the way to the 10. You mean for part C, for the last part? Okay, so it actually came from, so let's go back to the theorem, the remainder estimate for the integral test. So we know that the error is between the integral of f from n plus 1 to infinity and the integral of f from n to infinity. Okay, so now if you add Sn to both sides, Rn plus Sn is S. So if you add Sn to both sides, Sn plus that, Rn plus Sn, and Sn plus this, now you will have S in the middle, right? This is gonna be S. Now in the next page, we show that Sn plus the integral of f from n plus 1 to infinity is less than or equal to Rn plus Sn, which is the actual sum, and that is less than or equal to Sn plus the integral of f from n to infinity. And this inequality is what we use for part C, and this came from the last step over here. Okay, so this is how we obtained it, and this is the inequality we use for part C. So now if you use it for 10 terms, because we use 10 terms to estimate, now you will have S10 plus from 11 to infinity f of x, S, and then S10 plus from 10 to infinity to infinity. From 10 to infinity, the integral of f. And the integral of f, we figured that the integral of f is actually here. The integral of f turned out to be 1 over 2n squared. So if you want to calculate the integral of f from 10 to infinity, it will be 1 over 2 times n squared, 1 over 2 times 10 squared. And if you want to calculate the integral of f from 11 to infinity, it will be 1 over 2 times 11 squared. Does it make more sense now? Or do you have any other questions? No problem. Okay, I'm gonna do one more example, and then we'll finish the session. Estimate two n plus 1 to the power of -6 correct to 5 decimal places. There are different versions of this problem. Sometimes instead of estimate, they say round. It's exactly the same problem. Now let's state a small fact, which is going to be helpful in this kind of problems. To estimate or round a series correct to k decimal places, the error should be less than 5/10 to the power of k plus 1. And here is the reason. If you're trying to estimate a series, or even just think of a simple number. If you're trying to estimate it correct to 5 decimal places, then the error you make in the 6 decimal place should be less than 5. Because if it's greater than 5, then the last digit will round up, and then your 5th decimal place will change. This is what I mean. So let's assume this is a decimal number with 5 digits. So the 6th decimal, if this guy is greater than 5, you need to update the 5th decimal place. If this guy is less than 5, then you don't need to update it. So that's why when we're approximating the series, or 6 decimal place should be less than 5. If we're trying to approximate correct the 5 decimal places, I generalize that fact as k decimal places. It's going to be 5/10 to the power of k plus 1. In other words, the 5 at the k plus 1's decimal place. Okay, so this is going to be the idea. Now let's solve the problem. So we'll have 2n plus 1 to the power of -6, and we know that the error Rn is less than from n to infinity, and we want this error to be less than 5/10 to the power of 5 plus 1, because k is given as 5. Okay. Now, what is f of x, the corresponding function? It's going to be 1/2x plus 1 to the 6th. So let's try to integrate this function from n to infinity. It will be limit as t goes to infinity from n to t 2x plus 1 to the power of -6 dx. And to integrate that, you need to use u sub. And if you update the boundaries, I think when x is n, u is going to be 2n plus 1. When x is t, u is going to be 2t plus 1. So this integral will turn to running out of space. 2t plus 1, 2n plus 1. Maybe I'm just gonna move to the next page. Right? Because dx is going to be d over 2, and 2x plus 1 is u, and this is 6. It's hard to say. So if you pull 1 over 2 out and do the integration, you will have u to the power of -5 over -5 from 2t plus 1, from 2n plus 1 to 2t plus 1. And also we can pull out -5, -1 over 10. The limit as t goes to infinity, 2t plus 1 to the power of -5 minus 2n plus 1 to the power of -5. This is going to be 0 because it's infinity to the negative power. So long story short, we'll have two n plus 1 to the power of -5 over 10. And we want this guy, remember, we want it to be less than 5 over 10 to the 6th. So one thing you can do, I think you can simplify the 10 and 10 to the 6th. So five over 10 to the 5th will be, this is going to be 1. I think it will be 20,000 because this is 100,000. Yeah, so this is going to be 20,000. So 20,000 is less than 2n plus 1 to the 5th. So if you take the 5th root of both sides, and then solve it for n, I think n will be less than 3.12. So it turns out we need 4 terms to approximate the series correct to 5 decimal places. Then let's finish the problem. We need first 4 terms. Oh, just 4. So if you plug 1 for n, then 2 for n, and 3 and 4 for n, if you add them up, I think it will be 0.00145. And this is correct to 5 decimal places. So let's quickly go over it. As we said, if you're trying to estimate a number or a series, any mathematical expression correct to a certain decimal places, then the error should be less than 5. Error should be less than the half of the next digit. In other words, 5 over 10 to the power of k plus 1. So we want the error to be less than 5 over 10 to the k plus 1. In this particular example, it's 5 over 10 to the 6th. And what do we know about the error from the remainder estimate theorem? The error is always less than the integral of f from n to infinity. Then let's try to calculate the integral of f from n to infinity. If you use your improper integral knowledge, a little u sub and then limit, you will have 2n plus 1 to the power of -5 over 10, and that will be less than the error we calculated, 5 over 10 to the 5th. If you solve it for n, you'll see n should be greater than 3.12, so n should be at least 4. So you need 4 terms to have an approximation that is correct to 5 decimal places. Then add up the first 4 terms. It will give you 0.00145. And that's what I have to say for today. Does anybody have any questions? I hope everybody has a good weekend. I will post these notes on Canvas.